This is a ortho effect that we have observed in our chemical laboratory. So our students has worked on this substrate, and we have a very interesting finding in this regard. Let's say just focus on structure number one, where this is X. This X may be different. Let's see if this X is oxygen. Mean what we are having, we have an oxygen present at this position. We have this is a CH2, CH2, but oxygen CH3. On other side, this X may be a CH2 group. This is a difference only. So if we react this with nitrogen pentoxide, if you remember, this is a nitrating agent. So if we are using this one, then we get nitro product as dominating one. But if we are nitrating this, if this X is a CH2 group, then para product is dominating. You see it is 81% we get. 89% we get when this is this one. So what is going on in this case? Just the presence of this X group is making that big difference. That two isomer, this is called ortho isomer is dominating. Although this group is statically much crowded, it should orientate these two para position that we are observing in this case. In this case, you see this is N-butyl group, statically very crowded. It is favoring nitro at para, 81% product. The same we are expecting here, but it is totally opposite. Ortho product is 89% rather para. So what is going on in that case? In fact, this is showing a effect that you shall see in substitution reaction, commonly called enchimeric assistance, also called neighboring group participation. You shall see in substitution reactions later. But this effect has been done. What this oxygen is playing here? This oxygen, if you remember, have a non-bonding electron pair present. So nitrogen pentoxide, when leaves in such form, rather it generate NO2 plus charge. This oxygen donates this electron paired with the nitronium ion, and positive charge is on oxygen, and this nitrogen is bonded with oxygen. Aromatic substitution takes place. No, because this group is closer to ortho, this group is far away from para. No, it cannot transfer this nitro to this group. So that is the reason why this nitro is oriented at this position. If you remember, this is making a six-member transition state: nitrogen, oxygen, carbon, 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 carbon. Four carbon, one oxygen, one. This is making a six-member ring transition state. So this is the reason this nitro is oriented at ortho position, right? So if this bond is not formed and nitronium ion directly adds to this, 11% is due to that reason. So normally you see major isomer is this one, 89%, in which this group is making a big difference in such a case. This is called ortho effect. So I have a suggested reading for you, chapter number 21 and 22, different pages. You can read this out. So this will be very useful for you for this type of aromatic electrophilic as well as nucleophilic substitution reactions. So I escape, and I shall start the others what I have sent yesterday. So we shall focus on aliphatic substitutions at the moment. Everybody can see this slide.
Yes, sir.
Substitution reactions. Right, so in this case, we have covered, in fact, the very first aspect. This is the same slide you have seen in previous set of experiments. Just hold on. Right, so this is the very first set that you have already come across, just we have finished right now, that electron-rich substrate, aromatic substrate, electron-rich reacts with an electrophile, forming products. On the other hand, if the same substrate is electron deficient due to the presence of minus R group, or maybe more than one minus R group is present on this, then this X normally halogen, maybe triplet, maybe bromylate, and maybe any other good leaving group. It may be substituted because now this carbon or this aromatic system is electron deficient, not electron rich. So a nucleophile can react. This is called nucleophilic aromatic substitution reactions. This is electrophilic electrophilic aromatic substitution reactions. So these are the two different ways you have come across. Just we finished these mechanisms associated with certain rules associated with this, etc. Next task is when we are having carbon which is electron deficient, but this carbon we are doing the substitution on sp2 hybridized system, mean aromatic system. But here we are focusing on sp3 hybridized carbon, the substitution on sp3 hybridized systems. So if this carbon is electron deficient, how it can be deficient? If let's say X is an electron withdrawing group, it is not carbon, it is something which have high electronegativity than carbon. So it may be any such group, maybe oxygen, nitrogen, sulfur, phosphorus, or anything else, halogens. So if it leaves, then nucleophile shall be required. Electron-rich entity shall be required to substitute, to replace this X group from here. So this is called nucleophilic aliphatic substitution reactions, normally called SN reaction, substitution nucleophilic. But on the other hand, you have also already come across, if we have a keto form, this keto form is in equilibrium naturally with enol form. If we react enol with a base, so it base pick up this proton from here, results in the formation of this electron is transferred here, and this electronic density is transferred. Now look, focus on this carbon where I have a cursor, which is this carbon where this hydrogen has been transferred. This is also sp3 hybridized carbon. But this sp3 hybridized carbon under the effect of a base is totally opposite to this carbon. This is sp3 hybridized, this is also sp3 hybridized. This carbon is attached with an electron withdrawing group. This carbon is also attached with an electron withdrawing group. This is sp3 hybridized, this is also sp3 hybridized. Both are same, but they are unequal. Here, presence of a nitro group, presence of a ketonic group, aldehyde group is making this in enol form. This enol form reacting with the base is making up electron increase in electronic density at this position, which is this one. So this carbon, which is electron deficient here, we have converted into electron rich entity. Now it is not going to react with a nucleophile. It is electron rich. It shall definitely react with an electron deficient entity. So these are the two aspects we are going to discuss this. A little bit such aspect we have already come across in aldol reactions, in which we are using this as a carbanion. As a nucleophile, we are using adding to a aldehyde or a ketone system. You have seen the aldol reactions already in addition reactions. Their perspective was aldehyde or a ketone. But if we are taking, this was acting as a nucleophile. But now its perspective shall change. We shall take this as substrate and we shall take this as a reagent. It shall be totally opposite. Then it shall be called substitution reaction. So what we are going to do, we are substituting this hydrogen by a electrophile. Here we are substituting this X by a nucleophile. This is a difference. Here this sp3 hybridized carbon is electron rich in this substrate. Here in this case the electron, this carbon is electron rich, which is also sp3 hybridized carbon if you look at this one. So anyhow, this is the strategy. First, we shall discuss mechanisms involved with these systems. Then we shall switch over to these and we shall have a by name reaction, so many that I have highlighted in next slide. Just focus here. So I'm just going to classify these mechanisms. So we have here splitted these substitutions aliphatic. This system is called aliphatic. If you have sp3 hybrid, no undouble bond is present here. So this is called aliphatic system. This is aliphatic system. There is an unsaturation here, but this system where substitution is taking place, this is aliphatic. This is called. So this is aliphatic carbon, this is aliphatic substitution, but aliphatic nucleophilic and aliphatic electrophilic substitution, these are the two general categories that we shall highlight here. One is substitution nucleophilic, other is substitution electrophilic, but both are done on aliphatic systems. Substrates are aliphatic in nature, mean sp3 hybridized carbon. So first look at substitution nucleophilic. The one we have presented in the left hand, mean our substrate is electron deficient reacting with a nucleophile. So we have three different set of mechanisms, although I shouldn't call three different kinds. All of them are different from each other as well. So I have generally highlighted them on the basis of nature of substituent, nature of the aliphatic system. It may be SN2, SN1 or SNI. These are the abbreviation. SN2 stands for substitution nucleophilic. SN stands for substitution nucleophilic. SN2, SN substitution bimolecular. These two are one. It is showing the molecularity, mean the order of reaction. So SN2 means substitution nucleophilic bimolecular, substitution nucleophilic unimolecular. SNI, so this is substitution nucleophilic intramolecular. This is entirely different. So these are the three. And SN2 prime, SN1 prime, SNI prime. This is substitution nucleophilic bimolecular with rearrangement. This prime differentiate it from SN2. SN2 is normal. SN2 prime for a allelic system, you shall see. I shall explain this with the example. That's why I have differentiated these three differently, these three differently, and these three differently. Why? Because here we need a substrate which is entirely different from here. And if we are working on this, the substrate nature shall be different in this case. So on the basis of substrate nature, they are totally different. So SN2CA, it stands for substitution nucleophilic bimolecular conjugate acid. This shall be entirely different mechanism, entirely different aliphatic substrate we are using for that. SN1CA, this stands for substitution nucleophilic unimolecular conjugate acid. CA stands for conjugate acid. And last one, this is the neighboring group participation. This is also called enchimeric assistance. So both are same, no change at all, no difference. Similarly, TD mechanism, you shall also come across. Ion pair mechanism, this you shall also come across. So anyhow, this is just a layout I have presented for the substitution nucleophilic. And for substitution electrophilic, we have a variety of different mechanisms in which you shall see this electrophile shall be, this is the substrate which we are generating shall be the same. And these, where we are getting it react, it may be an ester, it may be an aldehyde, it may be a ketone, it may be a cyclic ketone, it may be a so many other type of substrates we are reacting with, and we shall get a variety of different products formation. So mostly these reactions are not explained because they have almost similar mechanism, just like rhenium mechanism you have come across. But how different electrophiles are generated, like for if you are interested to introduce Farmile group, we call that Wills-Meyer-Hawk reaction or simple Wills-Meyer. It may also be called Gattermann reaction, Gattermann-Koch reaction. Mechanism is same. Aromatic substitution mechanism is same, but how to generate an electrophile, that is different. So in Gattermann reaction, Farmile group is different. In Gattermann-Koch, it is different. In Wills-Meyer, this is entirely different. And Wills-Meyer-Hawk, it is entirely different. So anyhow, purpose is same, mechanism is same. So here, mechanism is also same for all, but what is different? Different scientists have used different aldehyde, ketones, esters, etc. So we can name them. This is a few of them as per the syllabi, because these are included in the syllabi, but it doesn't mean it is limited to this. There are so many other scientists who have worked in this field that we shall come across. We have missed here one which is called Robinson's annulation as well. So I shall also introduce Robinson's annulation in this. So this is called Claisen, is the name of a scientist. Claisen and Schmidt both contributed here. Perkin, a name of a scientist. Reformitsky, this is also a name of a scientist. Stobbs, this is also a scientist name. Darzan, Manish, Wittig, and Novolengev. All of these are the name of the scientists who vary the substrate and got different results. So we shall focus on this in much detail in upcoming lecture. So this is a just layout I have presented. You have come across aromatic substitution reactions. Now we have change over substrate. Now we are going to focus on aliphatic substitution. Our carbon shall be electron deficient, but sp3, you have seen aromatic system can be electron rich, they can be electron deficient. Similarly, sp3 carbon may be electron deficient, it may be electron rich in fact. So it shall be reacting with a nucleophile or it can be reacting with a electrophile. So these are the only four possibilities that you shall come across throughout the literature. That are aromatic substrate undergoing electrophilic substitution, or it is undergoing nucleophilic. If it is undergoing electrophilic substitution, it shall follow rhenium mechanism mostly, or sometime it may follow SE1 mechanism, substitution electrophilic unimolecular. Thirdly, very rarely, it may follow a simultaneous and departure mechanism. These are the three mechanisms only possible with aromatic system, which is electron rich. But if it is electron deficient, it can follow further three mechanisms that have been highlighted to you. One is a simple SN2 type mechanism, one is Benzene mechanism you have come across anyhow, simultaneous attack and departure mechanism you have come across before. So that is a different aspect. On the basis of aliphatic substitution reaction, when we have a sp3 hybridized carbon system, substitution is also possible there. So, but this carbon may be electron deficient, it may be electron rich. If it is electron deficient, it shall follow all these mechanisms that I have enlisted here. So these you can say almost a dozen of different mechanisms, 3, 5, and 4. So you can see 9 and 3, almost exactly 12. 1 dozen different mechanisms are possible. So how they differ from each other, we have a very thorough deliberation on that, and then we shall switch over to substrate which is electron rich, sp3 hybridized carbon but electron rich. So that is called substitution aliphatic uh, on aliphatic systems, substitution electrophilic on aliphatic systems. So this is so we shall start with in next lecture tomorrow with SN2 mechanism, substitution nucleophilic bimoleculars. This is also called Walden inversion, and this is always a concerted mechanism, single step.